Our speaker this morning is Amy Radunskaya, also called Dr. Rad by her students. Amy was, again, the president of the AWM. I'm not going to get the years right. Excuse me for being on Hawaii time, which is where I'm from. So I'm a little bit off, but I also feel like I'm a year off because I meant to be telling you all this stuff about a year ago. So in any case, Amy Radunskaya is currently a professor of Pomona, where she's been for many years. She's the past president, one of the past presidents of the Association for Women in Mathematics. She is also a professional musician, as well as being a professional mathematician. Her area of research is applied mathematics, mathematical biology, which is what she'll talk to us about today, and she got her PhD from Stanford. She has a long track record of great mathematical research. She also has a long track record of giving back to mathematics and creating and maintaining excellent programs, including the EDGE program. She's really one of these Wonder Women who's done it all. And what I hope that you get from that is not that you have to do it all, but that there are all these great ways that you can contribute to mathematics. You don't have to do everything that she does, because she's done absolutely all of it. But I hope you find something that you will help us do as well. Amy also, besides her fantastic research record and her record of giving to the mathematical community, is a fantastic expositor, and that's what we're going to be blessed with hearing today. She's going to talk to us today about between yes and no, looking beyond the binary from a mathematical point of view. So let's give her a very warm welcome.
Thank you for that awesome welcome. I hope I can live up to everything. I'm so happy to be here with all of you. And like Catherine, to have this as the first conference I've been to is perfect. All right. So this is where I'm from. Yeah, California. It's near Los Angeles. Come visit me. It's nice out there. Come visit me when you can. So I'm going to add to Catherine's land acknowledgement. I love this beautiful picture done by Marlena Miles. But we are on Dakota land, and I want to just say thank you for letting us be here and acknowledge that, you were promised a lot of things that the US government never gave you, and that the indigenous people will be here always. And thank you for letting us be here with you. So the title of my talk is sort of provocative, this, beyond binary thing, but really what I want to talk about is decision-making in an uncertain world. So when yes or no is not really possible, that there are lots of things in between. So reasoning, right, is usually associated with logic. But what does this mean if we live in an uncertain world? So I'm going to set up a kind of formal model for decision-making, right? You have ask the state of the world, and you have some actions you take, which you can think of as a function from the state of the world to consequences. So the decision maker has to choose this function under uncertainty, right? So it could be that they're uncertain about the state of the world. It could be they're uncertain about the consequences, even if they know the state of the world perfectly. And this is sort of where statistics, got its foundations. How can we make decisions without knowing exactly what the state of the world is or the consequences of those decisions? And also, the decision maker herself has beliefs and tastes, and we're going to just think a little bit about that to start with. So I highly recommend Foundations of Statistics by Leonard Savage as, thinking about what statistics means when statistics was first starting out. And Roy Radner's several papers of his on costly and bounded rationality. So I'll just say right up front, Roy Radner's my dad. He's turning 95 this month, and he was one of Savage's first students. So this is kind of a tribute in a way to some of the people I love. So also think about this as an act that the decision maker makes might be I need to acquire more information about the state of the world. And often that information is costly. And it turns out that there's where some of your personal biases or preferences come in. Like maybe I want information about a certain group, but not about, I don't want to pay that much to know about another group. That happens a lot in this world. So in order to even talk about decision-making under uncertainty, we need to quantify uncertainty itself, and that is probability. That's what it was invented for. The idea of chance is old. The Egyptians had played dice games like all through the centuries, but sort of the first known kind of written concerted effort to put probability in a mathematical framework was done in the 1700s, and here's one of those, Jacob Bernoulli's Ars Conjectandi, the art of guessing, really. And he is the one who invented this idea of expected value. So what's the average that you could expect? You're uncertain about consequences, but you could say maybe what's the average amount that you'll get, whatever. And he also noticed that if you observed something long enough, that the average of those observations would converge. And so that is what he's going to call the theoretical expected value. And they even put it on that stamp. Do you see that little wiggly line that's like converging? That's pretty cool. He called that the golden rule. Okay, so we're come back to expected value in a second. So what would rational decision-making look like in an uncertain world? Well, you'd want to sort of rank your choices and then pick the best one, right? So often choices or consequences are ranked by maybe utility, and the decision maker would choose the act or function that would maximize that expected average utility. So this requires a couple things: a probability scale, which is maybe personal, right? Maybe we don't all agree on what is the probability of certain states occurring, because you have to calculate that expected value. And then a utility scale for all those consequences. So economists call this the expected utility hypothesis. It's a hypothesis because it's not really known that that's how people act. In fact, I'll look at some situations where people don't really act that way. But let's get our heads into this for a second. So suppose you'll win $36 if you predict the sum of 2 dice rolls. So 2 6-sided die. What number would you predict? 7. Okay, why would you pick 7? Most likely. There's 6 ways you could get 7, right? So the probability of getting a 7 is, 1/6, and so you'll, on average, win $6. But if you bet on 2, there's only one way to get 2, and so on average, you'd win $1. So you'd pick 7, right? That makes sense, rational, right? So now let's think about this, another situation. Suppose you can buy a lottery ticket where you win either $1 billion for sure, or $1 billion with 89% chance, $5 billion with 10% chance, but you might get nothing at all with 1% chance. Which would you choose? How many people vote for A? How many people vote for B? Fewer, huh? But in fact, the expected winnings for B are larger. So why do most people do pick A? Why do they pick A? For sure, you'll for sure win $1 billion. $1 billion's a lot of money, that's enough, right? So we don't always maximize utility, obviously, or that utility, right? Now, how about this scenario? You'd win 0, so the percentages are supposed to be the same. You win nothing with probability 89.89, 1 billion with probability 0.1, 1 billion with probability 0.01, so on the left. But on the right, you could win 5 billion or nothing. So what would you choose? Here. B, right? It's the same difference in utility, but here, but for some reason, we'd rather pick, we're sort of, and this is a paradox. So this book by Diaconis and Skirms is called 10 Great Ideas of Chance. It's a really great book too. I got this from that book, but it's not really a paradox if you include in utility, your utility function, things about risk aversion or regret avoidance, okay? So there's something more to how we make decisions than just a calculation of expected value. There's some emotion. There's some emotion in this. So here's another example. Because we talk about risk and we talk about uncertainty, this sort of illustrates the difference. So you have two urns. One is the uncertain urn, which has 100 balls in it. Some are red, some are black. You have no idea what the proportion is. The other urn is the risky urns. You know 50 are red and 50 are black. You get to bet on the first ball drawn. Like you say, okay, you want to bet on red or black, and you get to bet. So which urn would you want to use? And which color would you use? Would you pick? So let's start with, which color would you pick for the uncertain urn? I don't know, we don't know, like whatever. Does it? What about the risky urn? I don't know, equally likely, right? Which urn would you prefer to play with? Okay, let's take a show of hands. Raise your hand if you'd like the uncertain urn. How about raise your hand if you'd like the risky urn? Well, a lot more people. In fact, that's normal. Most people choose urn 2. Weird, kind of. It's the exact same probabilities of red or black, right? But we are more uncomfortable with this uncertainty usually than with risk, because risk, you can measure. Sorry, just make sure I'm not forgetting to say something. Okay, so now that's so uncertainty, I think, is more uncomfortable because we can't, even if we observe many balls coming out of this urn, it's going to be really hard to tell what the proportion is of reds or blacks. Whereas risk, we can kind of assess by observation. I think that's the psychological difference. I'm not sure. So now I want to talk a little bit about biases in our choices. So here's a scenario. Deadly plague has emerged in a small community. If this plague is untreated, 600 people will definitely die. So doctors have two choices for two treatments, treatment A and treatment B. Treatment A, they will save 200 people for sure, exactly 200. Treatment B, they'll either save 600 people or no people. They'll save 600 people with probability 1/3. So same expected number of people saved. Which would you choose? You're a doctor. Let's say, how many people would choose A? How many people would choose B? More people would choose B. 600 saved. Okay, here's the same two alternatives, but just framed differently. Option A, 400 people die. Option B, nobody dies with probability 1/3. Now, does it make you change your mind? How many people would now choose option A? Yeah, so usually, usually this audience was a little different. Usually many physicians, and they've asked physicians this, would choose A in the first framing because you use the word saved. And B in the second because you say nobody dies. They kind of, interesting, right? So now that we've sort of thinking about it, well, people kind of make weird decisions, right? So maybe we should just get machines to make the decisions. They'd be better at it. But if we use algorithms to replace these, you might say, faulty decisions, what do we do if we have unsolvable problems, right? What do we do if logical consequences, are unknown? So here are some issues in this field they call bounded rationality, meaning that our rationality is bounded and we are irrational sometimes. And both sentient irrationality and machines, right? Because we program the machines, it's the same issue. So there's inconsistency, which we've seen examples of, ambiguity or vagueness, like we're uncertain about the state of the world or the way the question's phrased, unawareness, you're unaware of the state of the world or the consequences. And this is a really big one, failure of logical omniscience, which means that even if you know the state of the world perfectly, most of the time you won't be able to predict the consequences. The consequences are going to be unknown. And so, I mean, if, like, let's say you're faced with a math problem and you want to know a statement, and you want to know if you should prove it's true or prove it's false, right? How do you figure out which road to go down? Well, if we were completely rational, we should be able to figure that out right away. Would kind of ruin the whole fun of math, right? So also, let's think about some programs, say the one proposed by Polya, who thought that one could create a framework where you could measure the probability of any mathematical conjecture being true. And then you say, well, if the probability is high that it's true, I'm going to try to work on it, right? But this kind of, when we think about bounded rationality this way, it makes that program completely impossible. And so I think we're just keep going, doing what we're doing. Make sense? Okay, so back to the title of the talk, yes or no. I want to talk about deciding yes or no questions in the face of uncertainty. So I'm going to give a few examples first. So here's this really cute little creature, the axolotl, who is becoming extinct in the wild, even though it's a hugely important creature in parts of Mexico. They've been able to grow them in the wild, in the lab very successfully, but the wild ones may or may not go extinct. So how would we decide that? What information would we need? How would our emotions come into play? Here's an example from my research from a while ago where this anesthesiologist was trying to decide yes or no. So the patient comes in for a big operation, emergency operation. He has to decide whether they have obstructive sleep apnea or not. Why? Because if they do, then they need to, when they're put under, they need to have special observations, right? Because they're in particular risk. But often, how do you diagnose obstructive sleep apnea? You have to get someone in a sleep chamber to sleep overnight, count how many times they wake up and stuff like that. They don't have time to do that. The person's coming in for an operation right away. So we developed this Bayesian network. It's an algorithmic model, right? So you ask the patient all these questions like, do you snore? How do you get sleepy in the daytime? And then measures and takes their weight, et cetera. It also will matter what kind of surgery it's doing. And you feed all this stuff, and the Bayesian network updates probabilities of the event. Do they need special treatment? But really what it's doing inside is assigning probabilities of the various AHI, or the scores of sleep apnea. So that is something that someone has to decide this, right? So it's not like you can, I'm not going to say whether, you have to decide. This is very important for whether they survive or not. So we developed this tool to help, and it seems to have helped, at least in their hospital. Here's another example from my research. So this was proposed by Dr. Martin Frasch, who says that probably there are 2 to 3 times more cesareans performed than are necessary. And performing a cesarean is really hard on the body, et cetera. So he thought, well, we should try to predict whether they're actually going to need a cesarean. So this is predicting fetal distress. Now, when you're in labor, you have often you can have measure the fetal heart rate as a sign of distress, but you can also measure the brain activity with a very non-invasive kind of little thing. Now they stick on the baby's head. And so this is what he was wondering, whether with these two signals, you could predict fetal distress. These are some measurements he did on sheep. And how did we attack this problem? First, we came up with a mathematical model. This is a mechanistic model of both the heart rate and the ECOG. And then so we could simulate and then kind of study the model that way. That would be one way to predict if you have a model that you think is accurate and you can parameterize it to the patient, you could predict what's going to happen. Okay, so we'll come back to that idea in a second. Another way is sort of more data-driven. So you just look at the signals and you calculate something from the signals. This is one of my PhD students, Aisha Nahera, and she developed something called approximate cross-sample entropy. So taking the two signals, calculating this thing called cross-sample entropy to predict, and you can see in the panel in the middle, something different happens to that entropy, and that predicts, with enough time for the doctor to act, this distress signal that occurs a little later. So those are ways to make decisions. We're not sure, but it certainly adds to the information the doctor who's deciding has, right? So in our heads now we have these algorithms, but we also have our own, the experience and our own illogical, psychological choices. Here's another example, not my research, but this is just a COVID test, PCR test. And when you get a COVID test, they say, yes, you have COVID, positive or negative, but it's actually not just that. It's a number in between. So this is how they do the PCR test. They take a sample, right, and they put it in this test tube or whatever, and then they try to get it to replicate. And so on the horizontal axis is the number of replication cycles. And and it's only replicating the part of the DNA that matches the virus that they put in, okay? So then they see how much of that is replicating. They have to replicate it because it's so tiny. And so they go through many generations, and if eventually it exceeds a certain threshold, they say your test is positive. But it has to exceed that threshold within a certain number of cycles. So here you have the sample that tests positive, the one on the left, and then the one on the right are the controls. So they do some controls, and they say, okay, it took our controls 30 cycles, 28 cycles to go over the threshold, when the threshold actually is the inflection mark on that curve. So in the sample, if it crosses the threshold before that or within some distance of 28, they'll say positive. Okay, that's how they do it. They don't report how close it was to that edge. So like, what if you had something like this magenta curve, that was your curve? That would be negative, reported as negative, even though it was positive. Or what if you were positive, but just barely positive? Like, wouldn't you want to know that? I would. Like, I was kind of pissed off that I didn't get those numbers when I had one positive test, I had 0 symptoms. Like, really? Like, how close was it? Because maybe it's, so one of my things is I think we need to report these in-between numbers. You can say it passed, because often these yes or no tests are passing some kind of threshold, or is even the probability that we calculated above some threshold or not. So we've sort of touched on Bryman's Two Cultures paper. This is a very famous paper from early, like 2010 or something, where he says we have two kind of predictive cultures. One is, so our goals is right to predict a response and also to understand the culture. So one approach is just look at the data, fit a model to the data, parameterize that model, and then that gives you your probability of a yes. Think of it that way. The other way is an algorithmic model like the Bayesian network, where you have some algorithm you stick in your input and it does click, 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 like goes through this machine and comes out with we think it's a yes, maybe with a probability. I think both of these are valid, but I just want to talk a little bit about maybe bias in such models. So with both of those types of models. So here's an example that totally stolen from this guy's blog, Aaron Roth's blog, but I changed it up a little bit. So suppose you have a bunch of applicants that are going to be considered for an award. This is a music award, but it could be another award. And we want to give these people an award. We get to pick a bunch of them. I don't know how many. If they have innate talent above a certain value, right? And now we suppose, so above, say, 115. Suppose the innate talent in the population is normally distributed around 100, so we're picking this, upper bit. And then we can't observe talent though, right? All we can observe is some external measures. So we have two measures. One is a kind of long-term, over the past 4 or 5 years, how many concerts have you played, recordings, how are the ratings, kind of a long-term measurement. And another one is a test. You sign up for this virtuoso test and you play Tchaikovsky Rococo variations and they count how many mistakes you make. Okay, then that's another kind of talent. So then we're going to use those two measures to predict talent. And both of these are, let's assume they're normally distributed around your talent level after we rescale them with the same standard deviation. Okay, get the setup? So now we have two populations, red and blue. So the red, and they both have the same distribution of talent. The blue ones, though, have more money than the reds. And so they actually, because this virtuoso test, you have to pay for. So kind of, someone has to count the mistakes and all that. So they can take the test twice. They have enough money. That's the only difference between these two populations. And let's suppose also that the blues are a minority for now. Okay, so what happens? Well, if I simulate a bunch of, like, I don't know how many, 100,000 simulated scores I did. And then this is their virtuoso thing on the vertical and their long-term performance on the horizontal. The blue dots are the scores for the blues and the red dots are the scores for the reds. But except that the blues get, remember, the maximum of the two virtuoso scores. Well, how can we predict talent from this data? Because that's what we want. We want to pick the talented people. So if I assume a linear model, so this is sort of this data type model, I'm going to assume a linear model, do linear regression on the two variables and talent. And if I do them separately for the reds and the blues, I get, slightly different parameters. Makes sense because they're different. But the result is that it's more or less fair if you think of fair as having the same false negative. False negative means you weren't awarded the award even though you should have been. So if they have the same for both groups, we think that's pretty fair, right? Would you agree? Okay, so if we fit them separately, they sort of have more or less the same false negative. But now we're told, no, you're not allowed to consider color. So we have to fit them together. Not allowed to consider color in this. So we fit the data to one model, and then what happens is that the blues come out with the advantage. So you see here the top model, because when you fit a model together, it's going to conform more to the majority, right? That makes sense. So the blues are going to get more false positives, fewer false negatives, and more total positives, as opposed to the two models where you see the false positives and negatives are pretty much the same. So there's no bias in this at all. In fact, you might say, well, it's more fair to not consider color. But what we're doing then is losing information. So that's sort of a lesson of some sort. So what do we learn? So if we have two populations, different feature distributions, a single classifier, talented or not, they'll fit more to the bigger population. That could either advantage or disadvantage the minority population, depending on what the situation is. But there is no explicit bias either in the algorithm or in the decision makers or in the data gathering. It just is what it is, and we were hidden some information from us. So this problem of, it's kind of an ethical, can be an ethical problem. Like one example is organ allocation. You decide who gets organs, who needs them. How should you decide? Well, maybe you want to give organs to people who will benefit from them the most, right? And some people would say therefore we should take age into account, because people who are really old, well, they won't be able to use the organ for as long or whatever. But that's ageism, right? Doesn't sound very fair. So these are like really hard problems to grapple with. And it's easy to say, oh, something's fair or not. But I say we kind of often need a deeper look. Okay. So I want to just look at a few lessons over the last 20 years since Bryman wrote his paper. So he has three sort of morals. One is there are a multiplicity of good models. So how do we choose among many good models? I'm going to talk a teeny bit about that. Most people would say you choose, by Occam's razor, choose simplicity versus accuracy. That's what Occam would say. But Bryman says choose accuracy and then something else. And also there's dimensionality. Bellman says dimensionality is a curse, but actually sometimes if you use more dimensions, i.e. more information, you actually can make better and more fair decisions. So the Rashomon effect comes from a movie by Kurosawa called Rashomon, where 4 eyewitnesses give different versions of a crime. So it's just a word used to describe the situation where you have multiple models that are equally accurate, but give different predictions. Which one should you choose? So there's a whole theory behind this, which is really interesting, about Rashomon sets and how they're nested, how you can distinguish and navigate within those sets. This is an example. I just thought I'd give a really quick example more from my world of a Rashomon set so you can think about it. This is a SIR model, susceptible, infected, recovered model of a disease. So you have the susceptible people's catching the disease, becoming infected at a certain rate, and then recovering at a certain rate. And so I write down the 3 differential equations, there they are. And I need to estimate 2 parameters, beta, the transmission rate, and big D, how long it takes to recover from being infected. So I have some data, and I'm going to fit the model to the data, right? So here's my data. And typically, you're trying to fit this model at the beginning of an infection because you're trying to predict something, like how long will this infection last? Like when will we be able to go out again, right? So here's my data, the beginning of, and I fit the model using sort of least squares fit, some kind of, routine, minimization routine, gradient descent, something. Okay, that looks pretty good. I'm minimizing the distance. And so I say that's a pretty good beta and delta D pair. Oh, but wait a minute, this one fits just as well. So in our language, we say these parameters are unidentifiable from this data. In this paper by Damour and a whole list of people at Google, they call it underspecification. It's the same problem. And so one way you can deal with this, now sometimes you're stuck, so they define something called a Rashomon set, which is a set of all models that give you something very close within epsilon, which you define of the actual minimum that you could find. And so this is just a picture I made of a Rashomon set, so you could see the beta delta pairs that are pretty good. How do you pick between them? Because they give quite different predictions. And in fact, in their paper, they did the same example with fitting to a whole bunch of initial when you start these minimization algorithms, you pick a starting value and then it kind of minimizes, right? So this is what they got when they started with many different D values. And you see on the right how many different models fit equally well. So how would you then decide which one of all those models is correct? Any thoughts? Say what? Wait and see. Yeah, you could say, I don't know, like, let's just write it out. Any other thoughts? Maybe take an average. That is actually what a lot of people do. The one thing you might do is use that, you remember that cost function of gathering more information. You might say, well, what do we know actually about, say, the length of infection? I'm going to study that, or transmission rates. You might get some more information by understanding the disease itself. So just purely looking at data, sometimes you miss a lot of information. But there are other ways to navigate these Rashomon sets, and there's a pretty burgeoning literature on it. But one, there are arguments all the time about simplicity, so tractable models, interpretable models versus accuracy, which allows good prediction. So one approach is you first find the Rashomon set, so all these models are equally accurate, and then add constraints. Maybe you want a fairness measure in there. Maybe you want a robustness measure. So there's some good examples of these Rashomon sets in the sort of COMPASS data set. I don't know if anyone's heard of that, where they predict who's going to commit a crime again, and that affects judges' sentencing. And it was they had equally accurate models, but one predicted that Black people would commit crimes way more likely. And so maybe among all those models, you could decide some other constraints. And finally, really quickly, an example of humans in the loop. So we sort of saw that in a lot of medical decisions. You have these algorithms, and then in the end, the doctor is going to decide, and they may go against that prediction of the algorithm, or they may go with it based on their experience. So this is actually a cool experiment that came out by accident. They had a child welfare referral. So someone calls in and says, there's a problem, child welfare problem. Should you actually go out and visit and see what's wrong? Or is it kind of a crank call? They have historical records to look at that they could use as a predictive model. So they developed this, and they gave a referral risk score that the person on the phone could then look at and help decide, the call worker. And so it turned out that once they implemented this this predictive model, they noticed there was the call workers exhibited algorithm aversion and automation bias. So some people really they think the machine does better than humans. Other people think, I'm not going to let a machine decide anything about these kids. But on the whole, the referrals did change. So the algorithm was listened to, and it aligned well with what was actually happening in the homes. But then something happened. There was a glitch in the algorithm, and it put zeros in a whole bunch of places where it shouldn't have been. So there was this opportunity to then see how did the call workers react. And it turned out that the humans in this loop actually detected that glitch. So even though they trusted the algorithm in general, they also knew enough, had enough information, other information, to somehow detect this error. So this to me is like, I don't know, it's some kind of moral story that we don't want to take humans out of the loop completely. As bad as we are, as illogical, emotional as we are, we can sometimes help. So in conclusion, so I think that when we measure uncertainties, try and decide yes or no, it's really helpful to include that quantitative piece. It's not just yes or no, it's yes with this much conviction or this much probability or with this close to the threshold. Start with an open mind. So in probability, that would be a large set of priors. I didn't talk too much about model revision. So you have an idea of a model and you revise it as you go along. It turns out if your set of priors is big enough, you will always converge to the right thing. Don't ignore information. What is the proper notion of fairness? And also report, if you can, model discrepancy and ambiguity. So discrepancy means the number of model the number of data points in your training set that give different predictions. And ambiguity is the fraction of models that give different predictions. So there's sort of these two measures. And if you report that, as well as the prediction, it gives decision makers some additional information. And you could maybe look at those discrepancies further and you can tell, okay, tease apart what's going on. And also maybe consider having humans in the loop. And thank you for being here, getting up early, inviting me, and now you can all talk. Thanks.
Hi, Amy. Thanks so much for an interesting talk. I was curious about when you said knowing your COVID score close to the boundary would have been really helpful information to you. And I immediately thought of, I failed my glucose test when I was pregnant last year by 1 point. So like I had to do all these interventions just because I failed by 1 point. But I was wondering about, do you find a difference in human behavior if you actually know you're close to that threshold? Like sometimes I was unmotivated to do it because I thought, oh, I only failed by 1 point. How do you think that humans are affected by that information?
Yeah, well, I think it does affect your behavior, right? Because like you said, but I think that's good because it's like your behavior is changing based on information. Whereas if, let's say, you test positive for COVID, but you're really on the boundary, and actually your viral load, what's in it? But your test was positive, so you can't go to work for 10 days, and so you know, like I think it's, or in your case, maybe you did interventions that were unnecessary and maybe even harmful in some way because they're based on a kind of faulty or excessive diagnosis. So. You're right, your question's good, that like, how do you use that extra information? That will totally depend, and we may not even all agree on how to use that information, but it just seems better to have it, in my mind. Yeah, thanks.
Hi, my name is Helen Byrne. I'm from Seattle, so I'm glad I got up this morning. Your talk was amazing.
Thank you.
I'm really glad at the halfway point that you went into machine learning and algorithms. It kind of keeps me up at night that our students don't really have access to that in the first 2 years of college. Does that keep you up at night?
Well, I mean, that's kind of exactly why I decided to talk about this, because it's something that I've been really thinking about and worrying about. Because a lot of my research has been in mathematical modeling, and we write these models and we fit parameters, and this is a good fit. Yeah, it looks good. But starting to think about the yeses and nos and the maybes, I think is really important. So I don't know. I think we can introduce our students to these ideas early on. Like when I teach calculus, I do a little modeling. We can talk about this stuff. And I think more and more people are developing materials like that red and blue example. I just got off this guy's blog post, and there's lots of great examples out there. And maybe we can come together with resources to show people. That would be a good idea. Okay, thank you. Have a great day, everybody.